This problem asks us to determine the empirical formula for a compound. So we have our wanted quantity identified. Reorganizing our quantities, we see that we have values for 2 of our elements, but simply know that the remainder of our sample is oxygen. This means that our first step should be to subtract the 2 values that we do know from the whole, which is 100%, to determine the percent composition of oxygen. Our ultimate goal is to determine the mole ratios of the elements present in our compound. So we have to do something with these percent values that will put us on the path towards moles. Recall that if we assume that we have 100 grams of our sample, that the contribution of each atom is identical, whether we are discussing percentages or mass. This means that our percent values can be directly converted to mass values, which gives us a clearer path to moles. Now that we have gram values, we can convert from grams to moles of each element. This is a necessary step as we cannot compare grams of one sample to grams of a different sample. Manganese, phosphorus, and oxygen all have different molar masses, and so even if the masses of the 3 elements were identical, the atom count for each sample would still be different. We will never compare mass to mass at any point in this term. We will always need to move towards moles. Dividing each of the mass quantities by their respective molar masses, we come up with these mole values. Notice that I have included quite a few decimal places here. If you truncate your values too much with these problems, then you can end up with the wrong mole ratio at the end of them. You should aim for recording at least 4 decimal places for all of your intermediate steps. We now have values in moles, and we could set up ratios at this point, but it wouldn't do us a whole lot of good. Our empirical formulas are going to be in terms of the lowest whole number ratio, and these values definitely are not whole numbers. But if we divided all of them by the smallest value, we can get at least one whole number because anything divided by itself equals 1. The smallest value here belongs to phosphorus, so this is going to be our value of 1. What we do to one part of our equation, we will have to do to all the other parts, so you have to divide the moles of both manganese and oxygen by 0.56377 as well. Notice that we end up close enough to a whole number to round in the case of oxygen, but we really don't in the case of manganese. Many times we will come up with fractional values at this point in an empirical formula calculation. It's important that you don't round if you're too far from a whole number, because this 0.5 value here represents a known fraction, which is 1/2. This implies that all of our values are probably about half as large as they should be. So to get rid of this 0.5 decimal, we're going to multiply all of these values by 2. 2 is the reciprocal of 1/2, and this multiplication step effectively cancels out the fraction. We have to multiply all 3 of these values by 2, even though manganese is the only element with a fraction, because what we do to one part of our problem, we are going to have to do to all parts of our problem. At this point, we have a whole number ratio and can begin building our chemical formula. If you review the elements present, you should realize that you have a metal and some nonmetals. This really should make you think, I bet this is an ionic compound, which would cause you to place the cation first in your formula. Then place the rest of the elements in order of increasing electronegativity. You might get something that looks a lot like this. The most clever among you are probably looking at this and thinking, man, that's bonkers. And you would be correct, because as it is written here, that's a whole lot of atoms interacting directly with our metal cation, meaning that this formula likely represents the atom count correctly, but represents the actual bonding poorly. What we actually have here is 2 phosphate anions, and this formula would be best written as manganese 2 phosphate. This last step of moving from the atom count to recognizing the polyatomic ion is probably a bridge too far for a quiz question. But it's important to work towards this type of thinking because making it to that level means that you are likely ready to go for your quizzes.